In the global race to decarbonize our world and find reliable, clean energy, the conversation often circles back to a powerful, yet controversial source: nuclear power. For decades, the image of nuclear energy has been one of colossal cooling towers and massive, sprawling power plants. But what if the future of nuclear isn't bigger, but smaller? Today, we're diving into the world of small modular reactors, or SMRs. These compact powerhouses are being hailed by some as the next great step in carbon-free energy, promising to be safer, cheaper, and more flexible than their gigantic predecessors. But are they truly the answer? Or just a new chapter in a complex story? Let's break down the technology, the promise, and the very real challenges facing this new generation of nuclear power. First, what exactly are we talking about when we say small modular reactor? Let's break down the name. The small part is straightforward. The International Atomic Energy Agency defines SMRs as reactors that produce up to 300 megawatts of electricity. To put that in perspective, a traditional, large-scale nuclear plant often generates over 1,000 megawatts. So, we're talking about a facility with roughly a third of the power output and a correspondingly tiny physical footprint. This small size is key to their entire design philosophy. Next is modular. This might be the most revolutionary part of the concept. Instead of a massive, multi-year construction project on site, where every plant is a unique, bespoke creation, SMRs are designed to be built in a factory. Imagine a production line, like for a car or an airplane, but for reactor components. These standardized modules are then transported to their destination by truck, train, or ship, and assembled on site. This shift to factory fabrication aims to bring the efficiencies of mass production to the nuclear industry, promising faster construction, better quality control, and lower costs. Finally, the reactor. At its core, an SMR still uses the same fundamental physics as any other nuclear plant: nuclear fission. It splits atoms to release an immense amount of heat, which creates steam to drive turbines and generate electricity. However, the designs are far from old school. They incorporate advanced, often passive, safety features that represent a significant evolution from older generations of nuclear technology. So how different are SMRs from the traditional nuclear plants we're familiar with? The differences go far beyond just size. A traditional plant is a $10 billion plus investment that takes a decade or more to build. An SMR, with its lower upfront capital cost and a construction timeline of maybe 2 to 5 years, presents a much less daunting financial hurdle. This modularity also introduces incredible scalability. Instead of committing to a massive 1,000 megawatt plant from day one, a utility could install one 300 megawatt module and then add more units as electricity demand grows. This is a game changer for planning. One of the most critical distinctions lies in safety. Large conventional reactors often depend on active safety systems. These systems require external power and human intervention to work. Think backup generators and pumps that need to kick in during an emergency. SMRs, on the other hand, are designed with passive safety systems. These systems rely on the fundamental laws of physics, like gravity and natural convection, to keep the reactor cool and safe, even if all external power is lost. We'll touch more on that later. This combination of small size and enhanced safety opens up a world of possibilities for siting. Traditional plants need huge amounts of land and water, limiting them to specific locations. SMRs could be placed in remote communities, at industrial parks with high energy needs, or even on the sites of retired coal plants, allowing us to reuse existing transmission lines and a skilled workforce. Even refueling is different. While a conventional reactor needs to be refueled every 1 to 2 years, some SMR designs can operate for 3 to 7 years, or in some cases, theoretically up to 30 years without needing new fuel. SMRs are not a one-size-fits-all technology. There's a whole spectrum of diverse designs in development. Most of the designs closest to deployment are what we call Generation 3+. These are essentially miniaturized and advanced versions of the light water reactors that have been the workhorses of the nuclear industry for decades. They use water as a coolant and benefit from a long history of operational experience. A prime example is the NuScale Power Module, which has already received design certification from the U.S. Nuclear Regulatory Commission. But the really exciting developments are happening with what are known as Generation 4 reactors. These are a more radical departure, aiming for huge leaps in safety, efficiency, and sustainability. For example, there are molten salt reactors. Instead of solid fuel rods, the nuclear fuel is dissolved in a liquid molten salt, which also acts as the coolant. These can operate at much higher temperatures but at very low pressures, which inherently reduces the risk of explosive accidents. The liquid fuel also means certain types of meltdowns are physically impossible. Then you have high-temperature gas-cooled reactors. These use helium gas as a coolant and can reach incredibly high temperatures. This makes them extremely efficient at generating electricity, but more importantly, it means they can provide high-temperature heat for industrial processes that are currently powered by fossil fuels, like making steel, cement, or even clean hydrogen. Finally, there are liquid metal-cooled fast reactors. These use coolants like liquid sodium or lead. They operate at high temperatures and can be designed to breed more fuel than they consume, and even to burn up existing nuclear waste, potentially reducing the burden of long-term radioactive storage. This technological diversity is a key strength, allowing SMRs to be tailored for a wide range of applications. So what is the big promise here? Why is there so much excitement and investment pouring into this technology? The list of potential advantages is long and compelling. The number one selling point is enhanced safety. The emphasis on passive safety systems is a fundamental shift. Imagine an SMR module submerged in a massive underground pool of water. If a problem occurs and the reactor shuts down, the surrounding water will passively absorb the decay heat for days or even weeks without any electricity, pumps, or human action required. Gravity will continue to circulate water and heat will naturally convect away. This walk-away safe design philosophy aims to engineer out the possibility of severe accidents like those seen at Chernobyl or Fukushima. The second major promise is economic. Large nuclear projects are notorious for staggering costs and budget overruns. SMRs hope to flip the script. By moving construction from the field to the factory, developers believe they can achieve economies of scale, much like any other mass-produced good. Standardized, repeatable designs should lead to lower costs, shorter build times, and more predictable project budgets. The lower initial investment for a single module makes nuclear power accessible to a wider range of buyers and reduces the financial risk for any single project. Then there's flexibility. The modern energy grid is changing. The rise of intermittent renewables like wind and solar creates a need for reliable 24/7 power to keep the lights on when the sun isn't shining or the wind isn't blowing. SMRs can provide that firm, carbon-free baseload power. Some designs are even capable of load following, meaning they can quickly ramp their power output up or down to balance the grid as renewable generation fluctuates. This makes them a potential perfect partner for a renewable-heavy grid, not a competitor. But the potential of SMRs extends far beyond just putting electricity onto the grid. Many advanced designs produce high-temperature heat, a valuable commodity for decarbonizing heavy industry. This heat could be used for district heating, warming entire towns. It could power large-scale desalination plants, creating fresh water in arid regions. And perhaps most importantly, it could be used for the efficient, clean production of hydrogen, a fuel seen as critical for decarbonizing transportation and other sectors. SMRs could provide the clean, reliable heat needed to make industries that have been historically impossible to clean up green. Of course, despite this compelling vision, the path forward is filled with significant hurdles and valid criticisms. This is not a magic bullet. First, the economic case is still largely theoretical. While factory manufacturing sounds cheaper, the first-of-a-kind SMR projects are likely to be very expensive. Achieving those promised cost reductions requires a robust global supply chain and a steady stream of orders to actually get the economies of scale ball rolling. Critics also point out that by going small, SMRs lose the vertical scaling efficiencies of large reactors, which could mean the cost of electricity per megawatt-hour remains higher than other clean energy sources like solar and wind, which are continuously getting cheaper. And then we come to the biggest, most persistent challenge for the nuclear industry: waste. SMRs will produce radioactive waste, full stop. In fact, some analyses suggest that because of their smaller size and design, certain SMRs might actually produce a larger volume of nuclear waste per unit of electricity than traditional reactors. The world still lacks a permanent, long-term solution for the disposal of high-level radioactive waste, and SMRs do not solve this fundamental problem, though some advanced designs aim to mitigate it by burning waste. Navigating the regulatory and licensing process is another colossal hurdle. Most existing nuclear regulations were written for giant, water-cooled reactors. Adapting these frameworks for a dozen different novel SMR designs is a complex, time-consuming, and expensive process. Gaining the public's trust and social license to operate will be just as difficult. Then there are the security and proliferation risks. A future with thousands of smaller reactors scattered across the globe, rather than a few hundred large ones, presents a new set of security challenges. We would need to ensure the physical security of every single site, as well as the safe transport and handling of nuclear fuel, to prevent materials from falling into the wrong hands. Finally, there's the court of public opinion. Decades of skepticism fueled by high-profile accidents and the Cold War have left a deep-seated public anxiety around anything nuclear. The SMR industry must engage in a transparent, honest dialogue about both the risks and the benefits to have any chance of widespread public acceptance. Despite these challenges, the development of SMRs is a global race. The United States, Canada, the United Kingdom, China, Russia, and many other nations are pouring billions into research and development. Companies are partnering with governments, and demonstration projects are already being planned and, in some cases, built. This isn't a distant sci-fi concept, it's an active and emerging technological frontier. So, what's the final verdict? Small modular reactors represent a truly significant evolution in nuclear technology. They are not simply shrunken down old reactors. They are a rethinking of how nuclear power can be designed, built, and operated. The focus on passive safety, modular construction, and flexible applications offers a powerful vision for a clean energy future. SMRs have the potential to be a vital tool in fighting climate change, providing reliable, carbon-free power around the clock, and helping to decarbonize the toughest sectors of our economy. However, the journey from promising concept to widespread reality is still just beginning. The technology must overcome immense technical, economic, and regulatory hurdles. The intractable problem of nuclear waste remains unsolved, and the economic competitiveness against ever-cheaper renewables has yet to be proven in the real world. Ultimately, the success of SMRs will hinge on the ability of the industry and governments to tackle these challenges head-on. It will require continued innovation, unwavering regulatory oversight, and a deep commitment to public transparency. Small modular reactors are at a crossroads. They are a credible, potentially transformative technology, but they are not guaranteed to succeed. The coming years will be absolutely critical in determining whether this next generation of nuclear power can finally live up to its considerable promise and help build a cleaner, more sustainable world.